Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the vast expanse of space, there exists a whisper from the dawn of time, a faint glow that has traveled for over 13.8 billion years to reach our instruments today. This ancient light, known as the cosmic microwave background, or CMB, represents the oldest electromagnetic radiation in the universe, a fossil remnant from when the cosmos was merely 380,000 years old. The story begins in 1965, when two Bell Laboratories engineers, Arno Penzias and Robert Wilson, stumbled upon what they initially thought was an annoying hiss in their radio antenna. No matter where they pointed their horn-shaped receiver in Holmdel, New Jersey, the persistent noise remained. After eliminating every possible source, including cleaning pigeon droppings from their equipment, they realized they had discovered something extraordinary, the afterglow of the Big Bang itself. This discovery validated decades of theoretical work by cosmologists like Ralph Alpha, Robert Herman, and George Gamow, who had predicted that such radiation should exist if the universe had indeed emerged from an extremely hot, dense state. The CMB represents the moment when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing light to travel freely through space for the first time. Before this epoch, called recombination, the universe was opaque, a roiling plasma where photons could barely travel without being scattered. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Today, this primordial light reaches us as microwave radiation with a temperature of just 2.7 Kelvin, barely above absolute zero. Yet within this seemingly uniform glow lie the seeds of everything we see today: galaxies, stars, planets, and ultimately, life itself. The CMB isn't perfectly smooth. It contains tiny temperature fluctuations, typically varying by just a few millionths of a degree. These minute variations represent density differences in the early universe that would eventually grow under gravity's influence to form the cosmic web of matter we observe today. Measuring these fluctuations requires extraordinary precision. The Cosmic Background Explorer, or COBE, launched in 1989, first mapped these temperature variations across the entire sky. The results were so precise that project leader George Smoot famously described seeing the cosmic microwave background patterns as looking at God. COBE's success led to even more sophisticated missions. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, and the Planck Satellite, launched in 2009. Each mission revealed the CMB in greater detail, transforming our understanding of the universe's composition and evolution. The data showed that ordinary matter, the stuff of stars and planets, comprises only 5% of the universe. Dark matter accounts for 27%, while dark energy makes up the remaining 68%. These revelations emerged from analyzing the precise patterns of temperature fluctuations in the cosmic microwave background. But perhaps most remarkably, the CMB provides a direct observational window into the universe's infancy. When we observe this ancient light, we're literally seeing the universe as it appeared just 380,000 years after the Big Bang. The photons hitting our detectors today have been traveling through space since before the first stars formed, carrying with them information about the cosmos's earliest moments and the physical processes that shaped everything we see around us today. The cosmic microwave background represents far more than just ancient light. It's a detailed blueprint of the universe's fundamental properties, encoded in temperature variations so subtle they require the most sensitive instruments ever built to detect. Understanding how scientists extract profound cosmological insights from these minute fluctuations reveals the elegant interplay between theoretical physics and observational astronomy. The physics underlying the CMB begins with the concept of the surface of last scattering. This isn't a physical surface like the Earth's atmosphere, but rather a sphere in time and space, representing the moment when the universe became transparent. Before recombination, free electrons scattered photons continuously, keeping the universe opaque. When the temperature dropped to approximately 3000 Kelvin, electrons combined with protons to form neutral hydrogen, allowing photons to travel freely for the first time. These liberated photons carry information about the density and temperature conditions at recombination. Regions with slightly higher density were gravitationally compressed and thus hotter, while lower density regions were cooler. These temperature differences, typically just a few hundred microkelvin, imprint themselves on the cosmic microwave background as observable patterns across the sky. Scientists analyze these patterns using sophisticated mathematical techniques called spherical harmonic analysis. Just as any musical sound can be decomposed into its component frequencies, the temperature variations across the entire sky can be broken down into different angular scales. Large-scale patterns correspond to low multipole moments, while smaller angular features represent higher multipoles. The resulting power spectrum, a graph showing how much temperature variation exists at each angular scale, contains extraordinary information about the universe's fundamental parameters. The position and height of peaks in this spectrum directly reveal the universe's age, expansion rate, matter density, and the nature of dark matter and dark energy. The first acoustic peak, occurring at approximately 1 degree angular scale, corresponds to sound waves that had just enough time to compress once before recombination froze the pattern. This peak's position precisely measures the universe's curvature, whether space is flat, curved inward like a sphere, or curved outward like a saddle. Remarkably, observations show the universe is geometrically flat to within 1%. Subsequent peaks reveal additional physics. The second peak, at roughly half-degree angular scale, corresponds to regions that underwent one complete compression and rarefaction cycle. The relative heights of these peaks encode information about the balance between ordinary matter and dark matter. Ordinary matter, which interacts electromagnetically, affects both the radiation and matter components of these primordial sound waves. Dark matter, interacting only gravitationally, affects just the matter component. The Planck satellite, representing the culmination of decades of technological advancement, measured the cosmic microwave background with unprecedented precision. Its detectors, cooled to just 0.1 Kelvin using sophisticated refrigeration systems, could measure temperature differences of just a few millionths of a degree. The mission collected data for over 4 years, observing the entire sky multiple times to achieve the sensitivity needed for precision cosmology. Planck's results have transformed our understanding of the universe's composition and evolution. The mission determined that the universe is 13.8 billion years old, with an uncertainty of just 37 million years, less than 0.3%. The Hubble constant, describing the universe's current expansion rate, was measured as 67.4 kilometers per second per megaparsec. Perhaps most significantly, Planck's observations revealed subtle features in the CMB that hint at physics beyond our current understanding. These include slight asymmetries between opposite hemispheres of the sky and unexpected correlations at large angular scales. While these anomalies remain statistically marginal, they suggest that our picture of the early universe may be incomplete, pointing toward new physics that could revolutionize our understanding of cosmic origins. The cosmic microwave background not only reveals the universe's composition, but also provides our best evidence for one of the most remarkable theories in modern cosmology, cosmic inflation. This theory proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, growing by a factor of at least 10 to the 26th power in less than 10 to the negative 32 seconds. Inflation elegantly solves several puzzles that plagued early Big Bang cosmology. The horizon problem asks why distant regions of the universe, which should never have been in causal contact, have nearly identical temperatures. The flatness problem questions why the universe's geometry is so precisely balanced between expansion and recollapse. The monopole problem wonders why exotic particles predicted by particle physics theories haven't been observed. Inflation addresses all these issues by proposing that the observable universe emerged from a tiny, causally connected region that underwent exponential expansion. This process stretched microscopic quantum fluctuations to cosmic scales, creating the density variations we observe in the CMB. The theory makes specific predictions about the statistical properties of these fluctuations, predictions that match observations with extraordinary precision. The most direct evidence for inflation comes from the nearly scale-invariant power spectrum of CMB temperature fluctuations. Inflation predicts that quantum fluctuations in the inflaton field, the hypothetical field-driving inflation, should produce density variations with nearly equal power at all scales. Observations confirm this prediction, showing a power spectrum that varies as Ki to the negative 0.968 power, where Ki represents the wave number. However, the most definitive proof of inflation remains elusive: the detection of primordial gravitational waves. During inflation, quantum fluctuations in the gravitational field itself should have been stretched to cosmic scales, creating a background of gravitational waves that would imprint a characteristic signature. On the cosmic microwave background's polarization, CMB photons become polarized when they scatter off electrons during recombination. This polarization can be decomposed into two components: E modes, which create patterns that look like electric field lines, and B modes, which have a curl-like structure. Density fluctuations produce only E mode polarization, but gravitational waves generate distinctive B mode patterns. The amplitude of these B mode signals depends on the energy scale of inflation. If inflation occurred at the grand unification energy scale, approximately 10 to the 16th billion electron volts, the B mode signal should be detectable with current technology. The ratio of tensor fluctuations from gravitational waves to scalar fluctuations from density variations, denoted as R, provides a direct measure of inflation's energy scale. Multiple ground-based and balloon-borne experiments have searched for these primordial B modes. The background imaging of cosmic extragalactic polarization, or BICEP, collaboration operates telescopes at the South Pole, taking advantage of the site's exceptionally dry atmosphere and stable observing conditions. The Planck satellite also measured CMB polarization across the entire sky. These searches face extraordinary challenges. The primordial B mode signal is incredibly weak, potentially less than 1% of the temperature fluctuations. Moreover, our own galaxy produces polarized emission from dust grains aligned by magnetic fields, creating foreground contamination that must be carefully separated from the cosmological signal. In 2014, the BICEP-2 collaboration announced the detection of B-mode polarization, initially interpreted as evidence for primordial gravitational waves. However, subsequent analysis using Planck's dust maps showed that the signal was likely dominated by galactic foregrounds. This episode highlighted both the difficulty of the measurement and the importance of careful foreground subtraction. Current observations place strong constraints on the tensor-to-scalar ratio, with R less than 0.06 at 95% confidence. This limit rules out the simplest inflation models and suggests that if inflation occurred, it happened at energies below the grand unification scale. Future experiments promise even greater sensitivity. The Cosmic Microwave Background Stage 4, or CMBS4, project will deploy thousands of superconducting detectors across multiple ground-based telescopes. Space-based missions like the proposed Probe of Inflation and Cosmic Origins, or PICO, could achieve the sensitivity needed to detect gravitational waves from inflation or rule out entire classes of inflationary models. Despite the cosmic microwave background's extraordinary success in validating the standard model of cosmology, recent precision measurements have revealed puzzling discrepancies that hint at new physics beyond our current understanding. These anomalies, while statistically subtle, could represent the first cracks in our cosmic paradigm, pointing toward revolutionary discoveries about the universe's fundamental nature. The most prominent of these mysteries is the Hubble tension, AET, persistent disagreement between measurements of the universe's current expansion rate derived from different methods. When scientists analyze the CMB using the standard cosmological model, they infer a Hubble constant of 67.4 kilometers per second per megaparsec. However, direct measurements using nearby supernovae and Cepheid variable stars yield a value of approximately 73.4 kilometers per second per megaparsec. This 6% difference might seem small, but both measurements are now precise to better than 2%, making the discrepancy statistically significant at more than 4 sigma, meaning there's less than a 1 in 15,000 chance this difference arose from random measurement errors. The tension has persisted and grown stronger as both techniques have improved, suggesting a fundamental problem with our understanding of cosmic evolution. Several explanations have been proposed to resolve this tension. Early dark energy models suggest that a component of dark energy was present in the early universe, affecting the relationship between the CMB and the current expansion rate. Modified gravity theories propose that Einstein's general relativity breaks down on cosmic scales. More exotic solutions invoke new particles or interactions that were active during the universe's first few 100,000 years. Beyond the Hubble tension, the CMB itself exhibits several large-scale anomalies that challenge our understanding. The quadrupole and octupole moments, patterns corresponding to the largest angular scales in the sky, show unexpected alignments with each other and with the solar system's geometry. This axis of evil, as it's been dubbed, could represent a statistical fluke, systematic errors in the data, or evidence for new physics operating on cosmic scales. Another anomaly is the cold spot, a region in the southern galactic hemisphere where the CMB temperature is significantly lower than expected. This feature, spanning approximately 5 degrees across, represents a temperature deficit of about 70 microkelvin. While such a feature isn't impossible in the standard model, its probability is low enough to raise questions about whether it represents a genuine cosmological anomaly. The large-scale power asymmetry presents another puzzle. The standard inflationary model predicts that the CMB should be statistically isotropic, the same in all directions. However, observations show that one hemisphere of the sky has slightly more power in its temperature fluctuations than the opposite hemisphere. This asymmetry, while only a few percent, is inconsistent with the simplest inflation models. These anomalies have sparked intense theoretical work exploring extensions to the standard cosmological model. Some researchers propose that the universe underwent multiple phases of inflation, each driven by different fields and energy scales. Others suggest that quantum entanglement between our observable universe and regions beyond our cosmic horizon could create observable effects in the CMB topological defects, cosmic strings, domain walls, or monopoles, left over from phase transitions in the early universe could also explain some anomalies. These exotic structures would create distinctive signatures in the CMB, including specific patterns of temperature and polarization fluctuations. The most radical explanations invoke modifications to the fundamental principles of cosmology itself. Some theories propose that the universe's large-scale structure reflects quantum mechanical properties scaled up to cosmic dimensions. Others suggest that the CMB contains signatures of pre-Big Bang physics, offering a window into the conditions that existed before inflation began. Discriminating between these possibilities requires even more precise measurements and careful analysis of systematic effects. The Atacama Cosmology Telescope and the South Pole Telescope are providing high-resolution maps of small-scale CMB fluctuations. The Simons Observatory and CMB-S4 will achieve unprecedented sensitivity to both temperature and polarization signals. These observations will either confirm that the anomalies represent statistical flukes or systematic errors, restoring confidence in the standard model, or they will establish that new physics is indeed required to explain the universe's properties. Either outcome will represent a triumph of precision cosmology and our ability to probe the universe's deepest secrets through careful observation of its most ancient light. As we stand at the threshold of a new era in cosmic microwave background research, the next generation of experiments promises to push our understanding of the universe to unprecedented depths. These ambitious projects will not only test our current cosmological model with extraordinary precision, but may also reveal entirely new aspects of cosmic evolution that we can barely imagine today. The immediate future of CMB science centers on the Cosmic Microwave Background Stage 4 project, representing the most ambitious ground-based effort ever attempted. CMBS-4 will deploy over 500,000 superconducting detectors across multiple telescopes in Chile's Atacama Desert and at the South Pole. These instruments will map the CMB with sensitivity improvements of more than an order of magnitude compared to current experiments. This extraordinary sensitivity will enable CMBS-4 to detect gravitational lensing of the cosmic microwave background by intervening matter with unprecedented precision. As CMB photons travel from the surface of last scattering to our detectors, their paths are slightly deflected by the gravitational fields of galaxies and dark matter structures. This lensing subtly distorts the CMB patterns, creating a detailed map of matter distribution throughout cosmic history. By cross-correlating these lensing maps with galaxy surveys, scientists will trace the growth of cosmic structure from when the universe was just a few billion years old to the present day. This technique will provide the most stringent tests, yet of dark energy's properties, and could reveal whether Einstein's theory of general relativity accurately describes gravity on cosmic scales. The search for primordial gravitational waves remains one of CMB science's holy grails. Next-generation experiments will achieve the sensitivity needed to detect B-mode polarization signals corresponding to tensor-to-scalar ratios as small as r equals 0.001. This represents nearly a 100-fold improvement over current limits and would probe inflation models across a vast range of energy scales. Space-based missions offer even greater potential. The proposed probe of inflation and cosmic origins would observe the entire sky from the second Lagrange point, free from atmospheric interference and ground-based contamination. PICO's exquisite sensitivity could definitively detect or rule out primordial gravitational waves from grand unified theory scale inflation, potentially revolutionizing our understanding of particle physics at the highest energies. Beyond traditional CMB science, future experiments will explore entirely new frontiers. The cosmic neutrino background, predicted to contain over 300 neutrinos per cubic centimeter, has never been directly detected. These relic neutrinos, produced just 1 second after the Big Bang, would provide an unprecedented window into the universe's earliest moments. While detecting individual relic neutrinos remains beyond current technology, their collective gravitational effects on the CMB and large-scale structure may soon be measurable. The 21st century redshift, or 21 centimeter line of neutral hydrogen, offers another probe of cosmic history. Before the first stars formed, the intergalactic medium consisted primarily of neutral hydrogen that absorbed and emitted radiation at a wavelength of 21 centimeters. Future radio telescopes like the Square Kilometer Array will map this signal across cosmic time, revealing how the first stars and galaxies rionized the universe. Combining 21 centimeter observations with CMB data will create a three-dimensional movie of cosmic evolution, showing how the universe transformed from the smooth conditions revealed by the CMB to the complex web of galaxies we see today. This synthesis will test our understanding of dark matter, dark energy, and the physics of galaxy formation with unprecedented precision. Advanced data analysis techniques powered by artificial intelligence and machine learning will extract even more information from CMB observations. These methods can identify subtle patterns and correlations that might escape traditional analysis, potentially revealing new classes of cosmological signals or systematic effects. Perhaps most exciting are the unknown discoveries that await. Just as the original detection of the CMB opened entirely new fields of research, future observations may reveal phenomena we haven't yet imagined. The universe has repeatedly surprised us with its complexity and beauty, from dark matter and dark energy to the accelerating expansion and the multiverse implications of eternal inflation. The cosmic microwave background will continue serving as our cosmic Rosetta Stone, helping us decode the universe's deepest secrets. Each new measurement brings us closer to understanding not just what the universe contains, but why it exists at all. In this ancient light, we glimpse both our cosmic origins and our ultimate destiny, forever connected to the magnificent cosmos that gave birth to stars, planets, and ultimately to us.